Dear students, in the previous few turns, we have seen rank aggregation using, in the beginning, it was the Bodas method, and after that, we have adopted several fuzzy techniques for carrying out the rank aggregation. And at the end of the lecture, I had that study, or we will see how can genetic algorithm be employed for carrying out rank aggregation. So let us have a look at that today. So the first question and the foremost question is why genetic algorithms, right? Firstly, the positional methods are linear in complexity, no doubt. So that way they are better off. But the problem is that they neither optimize any distance criteria nor satisfy the Condorcet property. We have already considered what is Condorcet property. Condorcet criteria says if some element D belonging to the set defeats every other element in pairwise simple majority voting, then this element is ranked first. And this is necessary for spam fighting, right? So both the Condorcet criteria and how does it help in spam fighting, we have already discussed. We have said that any rank aggregation technique which satisfies Condorcet criteria will have any spam page going in the lower half if that page is not able to influence more than 50% participating search engines. If it is able to influence more than 50% participating search engines, then it is garbage in, garbage out situation. We can't do much. So I've elaborated that in detail already. So now our concern is how to have this distance criteria satisfied, because unless we satisfy the distance criteria, we won't be able to satisfy the Condorcet property, and we won't be able to do spam fighting. And in order to have the distance criteria, we have already seen that the fuzzy techniques or the positional Bodas method, they're all heuristic techniques, and they're not actually trying to minimize the aggregated Spearman foot rule distance, because minimizing aggregated Spearman foot rule distance is an NP hard problem for partial lists. For full lists, it may be done in polynomial time, but in our case of search engine rank aggregation, search engine results rank aggregation, it is NP hard because the lists are partial. We've already discussed all this. I'm just trying to connect you with what we are going to discuss today. So that is why genetic algorithms are trying to attack the NP hard problem of minimizing the aggregated Spearman foot rule distance for partial lists. Okay. So that is why we are employing genetic algorithm. The problems of the positional methods on one hand and the NP hard nature of partial foot rule optimal aggregation on the other motivate us to apply genetic algorithms for the partial foot rule optimal aggregation problem. Foot rule optimal aggregation for partial lists. We agree that GA-based techniques take more time, but we propose to provide the user with successively refined results from increasing generations of GA as long as the users keep waiting for the same. So if we have a look at how the genetic algorithm work, we have to have an initial population of chromosomes. Chromosomes are the solution, possible solution for a problem. So we try to code those solutions, preferably in binary, or we will see later in other bases also if required. So we have the initial such collection of solutions coded in binary. That is called chromosome. Then we carry out the survival of the fittest, that is based on an objective function. For our case, the objective function will straight away be the foot rule optimal aggregation, right? That will be objection. So what we do, around 50% of the chromosomes which are giving us the best or the least foot rule optimal aggregation distance, we will retain them, and the 50% will be simply eradicated using the survival of the fittest approach. Now those 50% remaining, there'll be crossover. For example, I have a chromosome, binary coded chromosome here, and I have a binary coded chromosome here. So what I'll do is I'll interchange a portion of these two chromosomes. So that way, when I interchange, these two will become 4 now. Okay, these two will become 4 now. Suppose this is 1 1 and this is 2 2, then I'll have 1 2 here and 2 1 here. Okay, so I'll have 4 of them. So this way 50% chromosomes which had survived, they will, using crossover, they will get back to 100%. And then there will be an additional step of mutation. Why we do mutation, I'll tell you in due course of time. But after mutation, we come back and we do the survival of the fittest on this 100% set of chromosomes. Again, 50% who are having a lesser foot rule optimal distance or the objective function will be retained, and the 50% who are not performing that well will be eradicated, survival of the fittest. So that is how chromosomes, then we have crossover, and then we have mutation. Okay, and this cycle repeats. This cycle repeats indefinitely, and this is called a generation. This is called a generation. Okay, crossover, and then in between the survival of the fittest will be based. Okay, just hold on. This should go here. This should go here. Okay, after mutation, it will be survival of the fittest, then crossover, then mutation. So it will be an indefinite cycle of having objective function evaluation for survival of the fittest, followed by crossover to make up for the 50% loss, and then mutation, and then again survival of the fittest. So that is one generation. This will go on indefinitely with the hope that each successive generation will be better than the last one, right? Those who are not better, they'll simply, eradicated in the test of the time or survival of the fittest. So that is what we are going to employ in our genetic algorithm based rank aggregation also. So objective function for genetic algorithm, for suppose we have 5 documents, let the full lists be this, and the partial list L1 with 3 be 214. We can complete this into a full list as 21435 and also modify L as 5412.5 to 2.5. This is basically average ranking method, if you remember. If you don't remember, please review that. I cannot repeat it every time, right? Now we can find the Spearman foot rule distance with the set of n partial list of documents, n such lists. The normalized aggregated foot rule distance is the objective function for our genetic algorithm, summing them up and dividing by n. We've already discussed all this. So this will be our objective function for genetic algorithm, and this will tell us how to do the survival of the fittest. Now, the first step, pool of chromosomes. We depart from having the pool of chromosomes represented in binary to those represented in decimal itself, because number one, each chromosome has to be a valid permutation of numbers 1 to mu. See, this has to be a valid permutation 5, 4, 1, 3, 2. If I do it using binary, suppose I write it as 101, 100, 001, 011, 010, then I may have several of these combinations which may not be valid permutations. Okay, so they do not qualify to be a valid chromosome in that case, because in all our cases we have to have a valid permutation, right? So it is not easy to have a one-to-one correspondence between a permutation and a binary representation. We can have it either by lookup, which means exponential complexity of memory, or by recursion, which means exponential complexity in time. Okay, so for a total of factorial mod mu permutations. Why I'm saying this? Factorial mod mu permutations, because I can have so many permutations. Suppose I'm having 1, 2, 3, so on up till u. So I have already discussed in one of the lectures, how can you list all the subsets of it? Okay, that will be mod mu factorial. So all these will leave so many of them which will be, which will not be tested at all, which will not be used at all, right? So I've just tried to make a little correction. It was overlapping. So now you can see it more clearly. So what I mean to say that I'm not going to use all these permutations. They may not be valid permutations at all. For example, the first one will be 0, 0, 0, 0, which means none of the documents will be listing there. Okay. So obviously 2 to the power these many bits patterns, that will result in no evaluation situation. Okay. I cannot have something like, okay, let me just pick the pen. I cannot have something like 1, 1, 1, 1, because that's not a valid permutation. I cannot have 2, 2, 2, 2, 3, 3, 3, 3. Or for example, I cannot, and further, I cannot have 1, 2, 2, because that is not a valid permutation. So I am looking for valid permutations only. So it doesn't make sense to code it in binary. What makes more sense is to do it in decimal. I don't say that it cannot be done in binary. I've already said that it can be done by using lookup, which means exponential complexity of memory, or by recursion, which means exponential complexity in time. So coding it in binary may be time complex as well as space complex. So that is why it makes more sense to use the decimal chromosomes only, decimal chromosomes itself. Now, when I'm using decimal chromosomes, how can I do crossover? Because I told you the technique for crossover is to exchange a portion of the chromosome. But if you do it, the resulting two chromosomes may not be valid permutations. They may not be valid permutations. So what we can do is we can make use of what is called in mathematics multiplication of permutations. It is defined like this, but let me take with the help of an example. When I say 312 into 231, okay, so what I'm doing is I'm trying to to place these in accordance with the positions here. When it says second position first, so second position over here is 1. Then third position, so third position is 2. And then first position, which is 3. Likewise, second position over here, which is 2. Then fourth position, which is 3. Then, third position, which is 4. And first position, which is 5. So when I do the multiplication of these two chromosomes, I get a valid permutation. When I do a multiplication of permutation, I get a valid permutation. Okay. So I can do crossover using multiplication of permutation, which is a standard technique in mathematics. And this leaves me with a valid permutation as a result. One thing you can notice that multiplication of permutation for your theoretical sake, I'm telling you that this is not commutative. Is commutative. We all know 4 into 5 is equal to 5 into 4. The numerical multiplication is commutative in nature. 5 into 4, sorry, 5 into 4. Both of them are 20, 20. But the multiplication of permutation may not be commutative. It is not commutative, in fact. Okay. So you can try doing 2, 3, 1 into 3, 1, 2. Okay. Let me do 2, 3, 1 into 3, 1, 2, and let us see what is the result. It says place the third document first. So third is 1. Then it says place the, okay, so in this case it is coming out to be the same. Okay, maybe when I try this one. Okay, let us try this one. What happens? If I do 2431 into 5243, so it says second position first. So our second position is 2. Then it says fourth position. Fourth position is 4. See? Okay, 2431 into 5243 is what I'm trying to do. So second position is 2, all right. But fourth position is 3. Is it also coming out to be the same? Let me see. Fourth position is 3, third position is 4. Again, in this case, it is coming out to be same. But I think multiplication of permutation is not commutative. However, it doesn't matter with us. It doesn't matter with us, right? Because we are doing multiplication of permutation in order to get the crossover done, right? And the technique I've already explained. How do I do that? Now, mutation. Mutation is carried out at a rate of 0.005 per digit per generation. This seems to be a very low probability. Then why at all do we do mutation? Try to understand this very carefully. Mutation is a process of taking the optimization path from the influence of a local minima. Suppose you are trying to minimize a problem, okay? Then you got stuck up in this local minima. Whenever you come here, you come here, and again you fall back into the local minima. So you're not able to get out of the influence of this local minima. So mutation is, in the case of binary chromosomes, converting any binary bit, flipping it from 1 to 0 or 0 to 1, so that you are somewhere here. You get somewhere out of the influence of this local minima. Once you are here, again, the successive generation will start taking you towards the absolute minima. But mutation should not be done with a very high probability or a high probability, because the path of descent that you are following, that will be disturbed if you do it with a high probability. Okay. From the real life, I give examples. Suppose there are two parents. The children are supposed to inherit the good properties of both the parents. In case the child doesn't inherit the property, the child may not withstand the survival of the fittest. But then there comes a surprise factor from nature. You know, you get so many good news. The son of a rickshaw puller qualifying IS. That is mutation. That is mutation. Okay, all of a sudden, from somewhere in the nature, you know, things change. So that surprise step or a jerk or a shake, that is called mutation. Okay. So the digit to be mutated has to be changed with the same restriction that the resulting chromosome remains a valid permutation. How can we do it? For this, the to be mutated digit is exchanged with any other randomly selected digit in that very permutation. Hopefully, okay, let me give you an example. Suppose I'm talking about 3, 4, 1, 2. Okay, and I have to do mutations. What I can do, I can pick up any 2 bits, any 2 digits, and I can interchange them. Okay, so mutation is done on a single chromosome, whereas crossover requires necessarily 2 chromosomes. Only then multiplication or permutation can be done, or the exchange of a portion of chromosome can be done. Okay, whereas mutation is done on a single chromosome in order to bring in that surprise input from the nature, so as to get out of the influence of the local minima and move towards the absolute minima or absolute optima, if you are more pleased with that. Okay, so I told you 3 main steps. The initial step is the initial population of chromosomes that we had decided to keep some randomly generated valid permutations. Then objective function evaluation for survival of the fittest. Then crossover for making up for the lost population, which was eradicated in the survival of the fittest. And then finally, the last step is mutation in order to bring in that surprise step if at all it has to be done in that generation with that low probability. And then we go back to again objective function evaluation, crossover mutation, objective function evaluation, crossover mutation. And this goes on indefinitely for, I can have 100 generations, 1000 generations. As we are having more and more generations, the result will keep on improving, as you will see in the result that I'm going to show you now. Our experimental procedure falls in line with the ones found in literature. We've already seen it when we were using the fuzzy-based techniques. So the same 37 queries, the same 7 search engines, the top 100 results, aggregating these results using our GA-based technique, comparing the aggregated list with the one obtained using Boda's method as our, as our benchmark. For all these queries, we have taken 1000 chromosomes in the pool for the GA. So 1000 chromosomes, 1000 randomly generated valid permutations from 1 to mod mu, where mu in our case will be 100, right? Or if I'm talking about the partial list, then it may be anything. From 7 search engines, coming from 7 search engines, it may go up to 512. It may go up to 600 something, because the results are not overlapping. So improvement in distance measurement with increasing generations of GA for 5 different queries. Each series corresponds to a query. You see, series 1 is 1 query, series 2, series 3, 4, 5. So you see, initially when there was the initial result, initial population of chromosomes, the distance was 0.52. But as we go on having generations, like after 20 generations for this query, it got to almost the absolute minima. But for the remaining, it may not have converged yet. So it keeps on minimizing unless it saturates to the somewhere near the absolute minima. So the more generations, the better the results get, right? For example, this particular series, whatever it may be, it saturates to near 60 generations, right? So more the generations, better will be the result, because the distance will be minimized further. So this is the value of the objective function, and these are the number of generations, right? So now if you want to see it in terms of numbers, so 7 search engines, 521 is the cardinality. What does that mean? 521 means 100 top results from all the 7 search engines. So 700 minus 521 must be the overlapping documents, and the remaining are not overlapping. Okay. So Boda's method gives me this, but after first generation, it is 0.5. After 10 generations, 0.5103. After 50 generations, it is 0.5061. Likewise, for query 2, 518 is the cardinality of the universe, right? Again, top 100 results from 7 search engines. Some of them may be common. So you count the common as 1. So obviously it will be lesser than 700, lesser than or equal to 700. If it is completely non-overlapping, this number will be 700. So again, you see the number improves for query 3. Of the 37 queries that I've listed above, the number decreases, keeps on decreasing. Okay. So genetic algorithm in each successive generation will give you either better results, or in the first case, the same result as the previous generation. The result never deteriorates in genetic algorithm. That is the beauty of it. Okay, that is the beauty of it. Okay. So now we are moving towards a very interesting architecture for a personalized web search engine. Okay. User issues a query. The query handler gives it to n search engines on the web and one web search by feedback learning that we have already studied. Okay. So that way it gives this query to n plus 1 search engines. Now all these results from n plus search engines are they undergo biased rank aggregation. By biased rank aggregation means Before aggregating, I'm biasing them or I'm putting a weight. And what is that weight? That is the search quality measure of the respective search engine. Okay. So that will come from the user profile. That will vary from user to user, how he or she is rating that particular search engine. So I'll elaborate, just keep patience. Now this aggregated result is presented before the user and the user feedback is collected. Implicit user feedback based on those 7 components, if you remember. Now this feedback does 2 things. First, this feedback contributes to web search by feedback learning, and also it evaluates the search quality measure of all the n+1 search engines, and the user profile gets updated. So now as this particular user keeps on doing it, what will happen? Learning will go into this feedback, and uptime may come when the search quality measure of all these 7, theoretically, all these n search engines will become 0, and the web search by feedback learning will have 1. So the result of web search by feedback learning itself may be the one which satisfies the user the most, right? Till such time, there will be having some finite values of search quality measure. So it will have biased search quality measure, biased rank aggregation. Okay. Okay, so in order to make you understand better, I have inserted a slide on biased rank aggregation. So let us see that. I've taken an example. Suppose there are 2 lists, L1, which is CDBAE, these are the documents, L2 BDECA coming from search engines having the search quality measures as Q1 is equal to 0.2 and Q2 is equal to 0.5. So let me select. Yeah. So Q2 is giving me, Q1 is giving me the search quality measure for this, and Q2 is giving me the search quality measure of the search engine from which L2 is coming. So we all know that the BODA score for A is 1, right? And over here it is 0, right? For B it is 2, right? So that way we go on finding out the BODA score for all of them. You all know how do we do that, okay? But before we actually sum them up, we try to multiply using their respective search quality measure also, right? For example, SA would be 1 into 0.2 plus 0 into 0.5. Okay, so 1 into 0.2 plus 0 into 0.5. So this is the biased rank aggregation score using BODA's method. Again, for SB, we all know it has to be 2, but we won't keep it 2. We'll keep it 2 into 0.2. So 2 into 0.2. And then over here, it will be 4 into 0.5. So 4 into 0.5. So this will be the BODA score. SC, there are 4 documents below it. So 4, but multiplied by its search quality measure, which is 0.2. So 4 into 0.2 plus 1 into 0.5. Okay, 1.3. Now we do the sorting. On their total scores, the combined ranking is which one is the maximum? B is the maximum. Then next is D, right? So this is 1, this is 2, then I have got 3, and then I've got 4, and finally this one is 5. So that is, I'll get B, D, C, E, A. So this is the biased rank aggregation that I'm talking about in the personalized web search engine. So you see, I've made use of all the different modules that we have learned so far. We have seen rank aggregation, and just now we have seen biased rank aggregation. So any of the rank aggregation technique you employ, I can always bias it. If you do it using BODA's method, I can do it. If you use it Shimura technique, I can do it. If you use it MFO, MBV, or Du Bois-Parete, if at all you want to, or even genetic algorithm. So I can do bias rank aggregation. The bias comes from the user profile, which contains the search quality measure. So now I can have two categories of users. There are the novice users who are satisfied with any reasonable result. For them, login may not be necessarily, because I don't want to have their personalized profile. The generic search quality measure will be taken in that case, and a generic relevance matrix will be taken for them. For the expert users, they want very focused, personalized results. For them, we will tell them to create a login. When they create a login, we'll take an agreement that we are going to store on their own hard disk the relevance matrix and their search quality measure profile. So whenever an expert user logs in and does a query, we go to N search engines, we go to the website by feedback learning using the relevance matrix used on his machine, stored on his machine. And we use the user profile of search quality measures according to that user is stored on his machine to do the bias rank aggregation. Okay, so two categories of users we'll have, right? Again, this will give you personalized results. Now remember, at some point of time we had discussed the problem of semantic ambiguity. Cricket, the insect, cricket, the sports. Now if you log in and you had been doing cricket, the sports, then your rank aggregation will ensure that you are getting cricket, these sports. If you are a zoologist, you will get the results corresponding to cricket, the insect. So that way, this is a personalized web search engine, which takes into account all the modules that we have discussed so far: web search by feedback learning, the search quality evaluation, and the rank aggregation or the bias rank aggregation. So all this is based on the user feedback. So I can classify this to be a user. If you remember in the beginning, we have said content mining, web usage mining, web content mining. So web content mining, we have seen the content based or the connectivity based, which included TF-IDF, vector space model, Boolean similarity measure as the content based, or the connectivity based for hub and authorities and page rank. But all that was web content mining. In the web usage mining, we have this search quality measurement, we have this web search by feedback learning, and this rank aggregation comes under both web content mining as well as web usage mining. So that is how I can do a broad web mining of the huge data that is available on the web. So we will stop here and we'll continue from here on the next turn. Thank you very much.